So today we will discuss some more basics of thermodynamics. Sorry. Let us start. So now we have to discuss like sorry, state of a system. So till here we have discussed. Now the next concept is work done on a system or work done by a system. So this is also like very important analysis we have to do related to thermodynamics. Work done on the system or work done by the system. Yeah. Work done on the system or work done by the system. Work done on or by the system. So let us quickly look at it, what it is. Work done on the system, work done by the system. So first let us make a system, then we will get an idea. So our system is basically a piston. It is basically a piston which is containing gas, which is containing some gas particles inside it. So I am just drawing it. So this is a kind of a container we have, and this piston we can compress it, stretch it. So this is the system. Now this system, in this system, exchange of energy can take place. Like meaning to say that heat energy can get outside, like from the system to the surrounding, or from the surrounding to the system, the heat energy can get inside. So heat transfer or energy transfer is possible. Like it is a closed system wherein exchange of matter is not possible, but exchange of energy is possible. It's a closed system. And this is the movable piston. I can compress it, I can stretch it. Like now, let us do some mathematics. like whatever we are observing, like we are looking at, here we are looking at it, that we will be writing mathematically. The observations mathematically we will write. So let us give it a try. We know that work done is equal to force into displacement. But here the work done will be force into distance moved in the direction of the force. In the direction of the force. Because whenever we apply the force on any object, and if that object moves some distance, then we say that okay, the work is done by the force. But if I am applying the force, but the object is not at all moving, then no work is done. So work done is force into distance moved in the direction of the force. Now here, in terms of force, if we look at, two forces are acting. Like let us suppose I am heating this system. I am heating this system. Heating means I am supplying energy. Because of which what will happen, the kinetic energy of the particles in the system will increase, and they will try to expand. Like they will try to expand, but there is an external force acting, that is the external pressure. It will avoid like this. So one is the external force which is acting, and one is the force exerted by the particles. So two types of forces are acting in the opposite direction. In this direction, we have force by the particles. We have external pressure. Now we can calculate one very interesting thing, that is the small amount of work done by the gas particles in expanding a small volume dV. So definitely in order to do a small amount of work, the force exerted should be equal to the external pressure, but in the opposite direction. So the force should be minus Px, minus Pex. Then only it will be able to expand. And because of that, a small change in volume is taking place. So the system is expanding a bit. So the small amount of work done will be minus external pressure into dV. So this I can write it like this. Whatever I got, this is signifying work done when the system expands by dV. Small change in volume against the pressure, against the external pressure, against the external pressure Pex. This is very clear. Now, if I want to find the total work, I know that I have to integrate it. If I integrate this dw, so the total work is the integration of dw, which is the integration of minus px dv from v initial to v final, which is further I can write it minus Pex I can take outside because it's a constant. External pressure acting is constant, and integration of one will be V itself. And when I will put the limits, I will get Vf minus Vi. So this result which I got, that I can say is the total work done. This is the total work done. Total work done by the system by the system. So this is very clear. Now here one very important discussion we should make, especially in numericals and all. Whenever system exerts a force, now here the system is the gas particles, they are trying to expand. It means that system is doing work on the surrounding. And when external pressure tries to compress the system, then we will say that surrounding is doing the work or work is done on the system. So work is done by the system and work is done on the system. Both the concepts are clear. So this is the concept of work done on the system or by the system. Now next concept we will discuss. Concept number 7. That is reversible process. In thermodynamics, this reversible processes plays a very important role. Reversible process. So let us try to understand what is meant by reversible process. So reversible process are basically processes, process that can be turned back. That can be turned back. Such that both the system and the surrounding. Such that both the system and the surrounding. Such that both the system and the surrounding return to their original states. Return to the original state. That is the main idea of reversible. To the original states. If I am able to return back to the original state, then it is reversible. With no change. And when I return back to the original state, there should not be any change. With no change anywhere else in the universe. So this is the main idea of reversible process. So I should be able to get back to the original state without any change in anywhere in the universe. Everything should be undone. There should be an undo button. But unfortunately, in real world, this doesn't happen. Like 100% reversible process, it is an ideal scenario. No processes are perfectly reversible. Like they're reversible to a very great extent, but when they reach to their original state, some changes will be done. No processes are perfectly reversible. And we call it like there is always an infinite infinitesimal modification is always of a value of any value.
So what does this mean?
This means that when we try to get back to the original state, a very minute modification takes place in the real world. Like in the see theoretically, reversible process, we should be able to get back to the original state without any change. Like there should not be any change. Everything should be as it is, as it was earlier. But in real world, reversible process do exist and we will study also. We are able to get back to the original state, but 100% that original state is maintained, that is not possible. Some changes will be there, some very small modification will be always. Like perfectly reversible processes are not possible in the real. Like friction, we can never get rid of the friction. So when I go from A to B and from B to A, once again I go, because of friction, some energy loss will take place. Always. Now let us look at some examples of reversible processes. Because these examples are very interesting to learn, to look into. So the first example which we can discuss, that is thermal equilibrium. Thermal equilibrium of two systems with the same temperature. And it is interesting. We will discuss it. So it is an example of a reversible process. Now it is very interesting to understand that how two systems with same temperature, they are exhibiting this reversible process. So let us try to understand this. Let us suppose I have a system A and I have a system B. We know that heat energy always flows from high temperature to low temperature. So if let us suppose the system A had a temperature T1 and system B has a temperature TATB. Let us suppose it's TA, let us suppose it's TB. Now I can say that if TA greater than TB, then the Q, that is the heat energy, will flow from TA to TB, isn't it? Or A to B. Q is the heat energy. Because heat energy always flows from body at high temperature to low temperature. Similarly, if TB is greater than TA, then net heat energy will be flowing from B to A. And but what about this? If both the temperature is equal, then tell me what will happen.
Then the heat will not transfer it.
Okay, yeah, so that is what we say, that if both that body are having same temperature, equal temperature, then no transfer of heat will take place because according to the law. But experimentally, we have observed that because in the laboratory when we try to analyze this experiment, we see that despite TA is equal to TB, we see that some heat energy is flowing from A to B. Also, some heat energy is flowing from B to A. And this is something strange observation we can see experimentally. So if it is happening, then heat is flowing from both the, like from A to B also and B to A also. Now, why it is happening, that we have to decode. So the idea is that now, see, TA is equal to TB. Perfect equality is a hypothetical situation that if the body A is having a 100°C temperature, then body B will be having exactly 100° is not possible. There will be 100.01, 100.0001. There will be definitely some difference will be there. And that difference can be so sensitive, which our measuring instruments might not measure also. But there will always be a difference. Because of that, whenever there is a temperature difference, heat will flow. And so that will be so minute, we ignore that. So ultimately, we say that equilibrium is achieved. Why equilibrium will be achieved, I will tell you. See, let us suppose TA is slightly less than, greater than TB. So some energy will flow from here to here, because of which TB will become increase. And it has to go from here. A cycle will be developed. Then TA will increase, then it has to go to TB. Then TB will increase, it has to cycle will go. And this cycle is what we represent on this. And this cycle is also representing the reversible state. Like A to B, then B to A. So once again, we reach the original state of A. Like from A to B we went, and from B to A once again we came to that original state. So it's a reversible. So thermal equilibrium is a reversible process. And why it occurs, that is also clear to us. Now,
Yes.
yeah, next example we can discuss for this reversible process. That is the reversible expansion. Reversible expansion. So this is the same diagram. I can copy it. So here also see the idea is that now both the forces they are acting. We say that they are equal to each other, but in reality they are not equal. Like exactly they are not equal. Like we say that here F is equal to Px. Like Px is the external pressure, and F is the force exerted by the system on the surrounding. And Px is the force exerted by the surrounding on the system. And we say that both are equal, but in reality, there is a difference because a very slight difference is that because of that, a net force will be acting. A net force will be acting. So how it will be acting is that sometimes F will be able to expand the piston a bit, and as a Newton's third law reaction, it will be once again compressing it and taking back it to the original state. Like let us suppose this is the original state of where the particle was in this point. Because of the net force, it will move to a certain distance, and once again it will get back to its state, and it will keep on going like this. And we call it as mechanical equilibrium. So there is a mechanical equilibrium between the uh, force exerted by the system and external force exerted by the surrounding. So this is the mechanical equilibrium. Isn't it? So this is the idea. So now we looked into uh, examples of reversible process is important. We should know that. Now we will look at the next concept, zeroth law of thermodynamics. Zeroth law of thermodynamics. So first, let us look what this law says, and let us try to understand it. First, let us look at what this law says. So, according to the zeroth law of thermodynamics, it states that if two systems are in thermal equilibrium with each other, if two systems are in thermal equilibrium, if two systems are in thermal equilibrium with each other, or with a third system. So, if two systems are in thermal equilibrium with a third system, and what it means, we will look at it. Then those two systems, then those two systems are in the thermal equilibrium with each other, are in thermal equilibrium with each other. This is the zeroth law. And it is very easy to understand, and it's very common sense, also logical. Like, let us suppose I have three systems. I'm writing it properly. So I have A, B. Now I am saying that two systems are in thermal equilibrium with each other. So I am saying that A and C are in thermal equilibrium. It will only happen, like I will say that let temperature of A be TA, it be TB, right inside of let it be TA, temperature of A, TB, temperature of B, TC, temperature of C. If A and C are in thermal equilibrium with each other, what it says that? It says that T of A is equal to T of C. Only then they will be thermal equilibrium. Similarly, B is in thermal equilibrium with each other. Let us, if B is in thermal equilibrium with a third body, that is the C, then what I can write? Temperature of B should be equal to temperature. Using these two equations, I can say from 1 and 2, I can say that TA is equal to TC. No, so TA is equal to TP, sorry. TA is equal to, which means that A and B are in thermal equilibrium with each other. And that is what this law says. The zeroth law of thermodynamics says that if two systems are in thermal equilibrium with a third system, then definitely those two systems will be in thermal equilibrium with each other. So this is the zeroth law of thermodynamics. So what is the significance of the zeroth law? Let us look at it. So basically, zeroth law, it helps us in measuring temperatures, like relative temperatures. So basically, zeroth law, it defines thermal equilibrium. Also, it helps us in defining temperature basis. So it defines thermal equilibrium. It forms the basis. Forms the basis for the definition of temperature.
So I didn't understand both.
Okay, this the significance you didn't understand. Okay. So see, the idea is that now the zeroth law, it talks about thermal equilibrium in that way that like see all the science which we have discovered or which we have invented, that is based on the observations, that is based on experimentations. Earlier, there was no concept of thermometer or some other measuring devices for temperature. Or earlier, the people were also unaware that what is the meaning of temperature, like how to define temperature. Now, with this zeroth law, we have one definition of temperature in that way that if like the statement in itself is telling that if two systems are in thermal equilibrium with each other, it means that their temperatures are same. So temperature is an entity, is any entity, unknown entity, don't know what it is, but it is similar to both A and B, something of that sort. So it tried to form a basis for the, and definitely it is not the exact definition of the temperature, but it can be the basis of the temperature. Like, okay, temperature is some unknown entity, but that unknown entity is similar for both the bodies, for both A and B. It is similar. From there, we can go to next level, next level, next level, and come up with a perfect definition for the temperature, which we already have. So zeroth law made an attempt. It formed the basis for the definition of temperature, and it defines thermal equilibrium. Because yeah.
Hmm.
Okay, so we got some idea about this zeroth law of thermodynamics. Now we will look into the next concept, first law of thermodynamics. So basically, first the law of thermodynamics, let us look at very important properties of it. And from now, like we are getting into the core of thermodynamics, like first law, second law, then third law, like law of entropy and all that. Slowly, slowly. So first law of thermodynamics is also called as law of conservation of energy. Law of and we know that law of conservation of energy states that energy can neither be created nor be destroyed, but it can only be transferred from one system to another system. Law of conservation. And in short, to be precise, we can say that the energy of an isolated system remains constant. Because isolated system is that system in which neither the exchange of matter is taking place nor the exchange of energy is taking place. So the law of conservation of energy, first law of thermodynamics says that the energy of an isolated system, the energy of an isolated system remains constant. So we can say it like this also. Okay. When delta Q, delta Q is like a small energy, is lost by a system, same amount, that is delta Q, is gained by other system, something like. And it's so interesting. Like, uh, just take any system, whatever its energy is there, it will be preserved. Like, if a chunk of energy is given to the surrounding, then it will be transferred. Like, energy is not neither created nor destroyed. Only transfer of energy is taking place. Now we have already seen that second point I can make. Like in thermodynamic system, in thermodynamic system, the total internal energy can be changed. In thermodynamic system, uh, total internal energy of the system can be changed via heat and work. Like I can supply heat, then internal energy will increase. And if I extract heat from the system, internal energy will decrease. And similarly, if I do the work, if the system does work, internal energy will change. And if the work is done on the system, then also internal energy change. And it's very important because ultimately, first law of thermodynamics is talking about conservation of energy. And in thermodynamic system, that energy is the internal energy or total internal energy of the system. Now, we should know how I can alter the total internal energy of the system. I can alter the total internal energy of the system either by altering the heat content or by the work. So, from this, we get the mathematical uh, definition of first law of thermodynamics. So, the mathematical definition of first law of thermodynamics, I can write it. Change in internal energy. U is the internal energy, delta U is the change in total internal energy of the system. It is equal to Q plus W. Now let us look at some sign convention. Then we will look at some more mathematics because there is always a confusion between Q plus W, Q minus W, minus Q, and all that. So this sign convention is very important. Let us focus on that. So we can have positive sign, we can have negative sign. See this positive sign, it indicates like positive and negative for W and Q. Let me write it properly. Let me write it properly. Sign convention for work done before that. Let me define the terms because everything is very important. This, so first let us define all this. What is Q? What is W? Let us define. And what is delta U? So Q is the energy transferred to the system. Energy transferred as heat to the system. That is the Q. Energy given to the system. And W is the work done on the system. And delta U is the change in internal energy
Yeah.
of the system. Internal. Now let us look at signs of WN. We can have a positive sign. We can have a negative. Whenever energy is transferred to the system or work is done on the system, then it is positive. Energy. Positive is energy transfer to the system. Energy transfer to the system. Work done on the system. Then it is positive. On the other hand, negative sign. Energy lost. The system can lose energy. Energy lost from the system. Energy lost by the system. Energy lost by the system, you can say that.
Work done by the system.
Yeah.
Work done by the system.
Work done by the system.
Negative.
That is right. Work done by the system. Energy lost by the system. Work done by the system. Work done by the system. So whenever the system does the work, the sign will be negative. Accordingly, we can alter this equation. Let us suppose in the numerical, it is given that the system is doing the work. And then we know that, oh, change in internal energy, if I have to calculate, then W I have to take minus. Because whenever system does the work done will be minus. The sign will be negative. Okay. So let me highlight this equation. This is a general equation wherein we are saying that heat is supplied to the system and work is done on the system. It's a general for the first law of thermodynamics, mathematical definition of the first law of thermodynamics. Now we will look at the next concept. Now we will look at the concept of enthalpy. Enthalpy. So in order to understand enthalpy, let us look at some background. Like we will derive the enthalpy. So one fact we know that, like we can try to understand the fact. The fact says that uh, if the pressure is constant, like if we do any work keeping the pressure constant, so whenever the pressure is constant, volume will change.
Hmm. If we
Constant
keep the
pressure, constant
pressure constant, then the volume will change.
volume will change to maintain the constant pressure. I will prove it. Let me bring back that diagram. Then you will get a feel of it. Visualization. This diagram we have to take it up. Let us bring it back. Now see, now what I'm trying to say is that the pressure constant, for example, if pressure is constant or external pressure or pressure, if pressure is, then in order to do a significant work, there should be some change, na? Like let us suppose pressure is constant, and I say that okay, I am doing the work on the system, or system is doing the work on the surrounding. If any sort of work is been done, that is possible only when there will be change in dimensions. Then there will be change in volume. Because what is work? Work needs displacement. Work needs some sort of like significant movement. Change in dimensions it needs. So if pressure is kept constant, it means that I cannot move this thing. It is fixed. The pressure is constant. So in, in order to do a significant work, I have to change the dimension of the system. And that is possible by changing the volume. I hope you are able, like what I am trying to explain, idea. So to be more precise, we can say that the work done, if work is done work done is under constant pressure, under constant pressure, it will lead to, or it will lead to change in volume. And that is what we did in this derivation also, wherein this force is exactly equal to external pressure, because of which we were able to achieve a very slight expansion.
Mhm.
And we said that, okay, work done is minus P external dV integration. So we were able to say this. So whenever work is done under constant pressure, there will be a change in volume. With this idea, with this idea, I can represent it mathematically, that work done is equal to minus P Vf minus Vn. And why minus P I am using? Because the force which will be doing work against the external pressure, it will be acting opposite to the P. Hence, minus is just representing the direction, that the force which will be doing the work against the external constant pressure, that will be acting opposite. So minus P and change in volume. So this is the work done. And here, interestingly, P will be constant. P will not at all change. Now we know the uh, from first law of thermodynamics, delta U is equals to Q plus W. So I can write, it will become U minus P Vf minus delta. Now, what is the delta U? Change in internal energy means UF minus UY. It is equal to U minus P Vf minus. Now I can reshuffle it to write something like this. UF plus P Vf minus UY plus PVI is equal to, and this U plus PV is the enthalpy.
Hmm.
Is called enthalpy of the system. isn't it? And we represent it with H. So we can say that from this equation, we can say that HF minus HI, where HF is the final enthalpy, HI is the initial enthalpy. So this I can represent as HF, this I can represent as HI. The difference of that will be Q. Or delta H is equal to, meaning to say that whenever, what is Q? Q is either the energy supplied to the system or energy lost by the system. So whenever there is a transfer of energy taking place inside the system, there is a change in enthalpy. So enthalpy is a parameter which gives us an idea. The change in enthalpy is a parameter which gives us an idea whether any transfer of energy is taking place or not, like transfer of heat energy, which is the heat energy. If delta H is zero, like we are solving a problem, there we are seeing that okay, delta H is zero. It means that no transfer of energy is taking place, no transfer of heat energy is taking place. And for isolated systems, delta H has to be zero. For isolated systems, delta H has to be zero. Now what we can do, once again, we can uh, get back to the first mathematical definition of first law of thermodynamics. Delta U is delta U, like change in internal energy of a system can take place only via either heat or work. So here instead of Q, I can write delta H, and instead of work done, I can write minus P delta V. Why minus P? Because now here work is done by the system, uh, in our example. So this is the one more form of first law of thermodynamics involving enthalpy, change in enthalpy, and change in volume. And this is applicable, this equation is applicable only for constant pressure. Whatever thermodynamic process we are doing, if we are doing maintaining the pressure constant, then only we have to apply this. Otherwise, it is not applicable. And from here, we can say that, delta H, change in enthalpy, is equal to change in internal energy plus P delta. All this below. So this was the concept of enthalpy. So delta H is equal to delta U plus P delta V. Now we will look at the next concept. That is heat capacity. And we denote this heat capacity by capital C. We denote the enthalpy by capital H. Capital. Now let us look at what is this heat enthalpy, like heat capacity. So the definition of heat capacity is, so quantity of heat required to raise the temperature by one quantity of heat, that is small q. Small q always represents heat. So quantity of heat required to raise the temperature raise the temperature of the system. Okay. Like in any system, if we introduce few heat, because of which increase in temperature will take place. So from T1, the system will go to T2. Now let us suppose if quantity of heat required is more, then we say that heat capacity is more. Now let us look at the mathematical definition for this. So heat capacity C is equal to Q upon delta T, T2 minus T. This is the heat capacity. Heat capacity is amount of heat energy required to raise the temperature of the system. So capital C is equal to Q upon T2 minus T. Now here two, three more some more very important terminologies we will discuss related to heat, the heat capacity. So there is a concept of specific heat capacity. Specific heat capacity. Specific heat capacity of the system. So it is quantity of heat quantity of heat small q required to raise the temperature. To raise the quantity of heat required. The quantity of heat required
1 degree.
by the system of mass 1 gram. By the system of mass 1. System of mass 1 gram. To raise the temperature. This is the specific heat capacity. In specific heat capacity, the system, the mass of the system is 1 gram. Similarly, we have one more very interesting concept, very important, molar heat capacity. Very important. In molar heat capacity, what we do, we take 1 mole of the system. 1 mole of the system. One mole of the system. So the idea is that quantity of heat required by 1 mole of the system to raise the temperature.
Yes.
And we can also write I can write it here somewhere. C is equal to dq by dt. Because that q, it is not needed that q may be constant. It can vary also because see what is q? Q is either heat, heat supplied to the system is the q. Now heat supplied to the system can be either constant or it can be a function of time or function of any other parameter. Like with time, the heat which we are supplying to the system it may increase exponentially. Then we have to use this equation dq by dt. That whenever function is given, like a heat is a function of time, so we have to differentiate that function with respect to temperature, something like that. Now, two things we have to look into, two more very important concepts. Molar heat capacity at constant volume and molar heat capacity at constant pressure. So when I talk about molar heat capacity, two scenarios are very important. One is the constant value, and one is the constant pressure. So let us first look at constant volume. You see, we know that when the volume is constant, then the work done has to be zero, no other way around. Because if volume is not changing, means no displacement is there. So at constant volume, work done will be zero. It is very clear. And hence, change in internal energy will only be equal to Q. No W will be. And hence, molar heat capacity, which we call as CV. CV means molar heat capacity at constant volume. It will become, instead of Q, I can write delta U. So partial derivative of internal energy with respect to temperature. This is applicable for constant volume. So this is the molar heat capacity at constant volume. Because instead of Q, I can write U. So U by T2 minus T1, and in terms of differential, I can write it like this. Now we can see the constant pressure. We can see the constant pressure. Isn't it? Constant. In constant pressure, to until like whatever we are discussing, we are mainly discussing keeping pressure constant. So there we know that change in internal energy, it will be Q, and we are assuming like the work is done by the system. The piston example which we saw. So minus
Yes,
W. And we know that that work done is P into delta V. So delta U is equals to Q minus P into delta V. That we have already seen. Now what will be Q? Delta U plus P delta V. And hence, and U plus PV is H. So we have already derived it now. Q is delta H.
yes.
So molar heat capacity at constant pressure, we can write it in the form of enthalpy. Delta H, and here the capital T is not the time but the temperature. Because we are so used to differentiate with respect to time that we should be aware that here we have to differentiate the equations with respect to temperature.
Yes, sir.
Now this is clear to us. Now we will look at the relationship between them. Relationship between molar heat capacity at constant pressure and molar heat capacity at constant. Let us do this. Okay, relationship. We know that delta H is equals to delta U plus delta P into V. If I divide all of them with delta T, I will write delta H upon delta T is equal to delta U. Let me write it properly. We may get confused with V delta PV by delta. And delta H by delta T is what is Cp, which we just now derived. And delta U by delta T is Cv, which we just derived. Plus delta P into V by delta. So this is the relationship between Cp and Cv. Okay. Now we can take it to the one more level. Like in thermodynamics, ideal gas plays a very important role. Like there are some gases which are close to ideal gas. Like they exhibit some properties related to that. So if we use that gas, then some special equations will be followed, and that is what we will discuss. For ideal gas, the basic formula which we have studied, PV is equal to RT. Like nRT, but number of mole we are taking 1. So PV is equal to RT. So I can say that delta PV, since R is a constant, delta T, R. So in the relationship, instead of PV delta, we can write R delta T. So the relationship will become Cp is equal to Cv plus R delta T upon delta T. And this delta T will cancel. So and this equation is applicable only for ideal gas. For ideal gas, Cp is equals to Cv plus R. Or I can also write Cp minus Cv, like molar heat capacity at constant pressure minus molar heat capacity at constant volume, this will always be a constant. That is the universal gas constant.
Yes.
This is the relation. Now some results you can use, like you should remember that we can use that directly, some very important results. Let us look at those results. I'm making a note. Just a minute. I'm making a note. CB is equal to V by 2R. And this is applicable for monoatomic ideal gas. Monoatomic means single atom. If a monoatomic ideal gas is given in the numerical, then CB we can take as 3 by 2R for monoatomic ideal gas. And the CP is 5 by 2R. For monoatomic ideal gas. For mono. So for monoatomic ideal gas, we have CV, CP, and we have something called as heat capacity ratio that we represent like this. It is the heat capacity ratio. It is equal to CP by CV. CP by, which is equal to 5 by. And this is also for monoatomic ideal gas. Isn't it? So this is done. So basically, we looked at heat capacity. So heat capacity concept is clear, and heat capacity is important. Like in terms of numericals, heat capacity is very important. So today we can keep it till here because the next topic which we will be having applications of first law, that we can start fresh.
Yes.
So let's conclude the session. Ending the stream.